Okay, so what exactly is a sampling distribution? We've talked so far about population distributions, right? There may be some distribution of some population parameter. Remember, we're talking about collecting all of the values that are members of that population and looking at a distribution. Visually, perhaps we may generate a histogram or something of the sort. We also have talked about sample distributions. Right? More commonly, the information we have will be data from a sample, a measure of some particular sample that we have, and we have measurements of each observation in that sample. And we, again, may generate a distribution of all the observations in that sample. Okay? The sampling distribution is yet another distribution. And it's probably the hardest one to get our heads around, and frankly, it's probably the hardest one to actually measure, to actually physically take. Okay? Why do we do sampling in the first place? I think we talked about this in our very first session. Usually it's because we either can't afford in terms of money or in terms of time to go out and measure every single element or member of a population. So therefore we take a sample, it's a smaller representative subset that we can afford in terms of time and finances and perhaps other things to measure. And then we do some estimation about our population parameter based on the sample. That's what we're doing in inferential statistics. Okay? So presumably the population distribution is going to be a lot harder for us to actually get our hands on. That would mean going out and measuring every single member of the entire population. Okay? Well, the sampling distribution itself is even more complex because it is a distribution of the sample statistic for every possible sample that could be taken of a given size from the population. Let's think about this for just a little while. What does that mean? So I have a given population of a certain size. Sample size, the population size is not necessarily important, but it's some population that's out there. I can take a sample from that, a random sample from that entire population, and I can find, let's say, the sample mean. All right? Now, I could go back and take a second sample and calculate a second sample mean, and a third sample, and a fourth sample, all of the same sample size. And if each of those are randomly selected, and they're representative of the population, each of those sample means is going to be a little bit different because I'm actually selecting different members in that sample each time. Okay? And for a population of any size, once we make the assumption that the population is much, much larger than the sample, then the possible number of samples that I could randomly select from that population is really, really large. Okay? Just think about it. And we'll see an example in a short while. But what we're talking about when we talk about the sampling distribution is imagining that we could capture every single sample that's possible, that's theoretically possible, of that same sample size, measuring the sample statistic, let's say the sample mean, for example, and generating a distribution of all of those sample means. Some will be larger than others, some will be smaller than others. They'll have some sort of peak to that distribution, some center of clustering. There'll be some sort of spread, just like is true of all distributions. And that distribution is the one we're referring to as the sampling distribution of the sample mean, or of whichever sample statistic we're looking at. And as you can imagine, just from the sheer number of possible samples, it is impossible in all practical terms to actually take and look at the theoretical sampling distribution. We can do it analytically and mathematically, but to actually go out and measure every possible sample that exists for samples and populations of any size is practically impossible for us, even more impossible than it would be to just go out and measure the entire population. But it turns out the sampling distribution is the key to understanding how we can go about estimating a population parameter from one single sample and the sample statistic that we measure from that one sample. And it really comes back to just the simple things we know about a distribution. So if we know something about that sampling distribution, if we know its mean, if we know its shape, if we know its standard deviation, we can say some very important things about the distribution, just as we saw with the standard normal distribution. We knew some things right off the bat about that distribution just because we understood distributions, right? And we understand symmetry, we understand standard deviation and mean. All right, so we're going to use that exact same approach. So it's created by taking many samples, theoretically all the samples of a population of the same size, calculating over and over the sample mean, or whichever statistic we're interested in, and realizing that those values, those sample means or sample standard deviation, again, if this is true for all sample statistics we could measure, those values are going to occur with a certain frequency distribution. And that distribution is what we call the sampling distribution of the sample statistic, and it will have an expected value, a mean, and it will have some kind of a standard deviation. So hopefully in your mind, and the video should have helped you with this, you're picturing now this distribution of all the possible sample means that we could capture from samples of a population. And again, the key is that all the samples have to be of the same size. And the relationship, the characteristics of that distribution are going to be different. What is the shape of the distribution? What is the standard deviation? What is the mean of that distribution, or the expected value? Well, those may all be different depending on what the sample statistic is. And as I said, the most frequent measure we look at is the sample mean as an effort to estimate the population mean. There are others. As we'll see, we'll do inferential statistics looking at the sample population in an effort to estimate the population the sample proportion in an effort to estimate the population proportion that meets some criteria. But the estimation of a population mean is one of the most important and frequent types of inferential statistics that we do. And the sampling distribution of sample means is governed by something called the central limit theorem. And this is one of the most fundamental theorems in statistics, and it tells us something very, very important. Okay? And here's what it tells us. That for a population that has a mean mu, or population mean, and a standard deviation sigma, right? What can we know about that sampling distribution? And I want to look at an example. It's our list of times taken to serve a customer at a drive-up window. And we calculated already the population mean for this list of observations, and the standard deviation. And for our purposes in this example, I'm going to treat this list of 200 values as a population. Okay? So I calculated the mean using the formula average, and I happen to have a label here for my data. That's why you don't see column and row indicators in here. I call this column data underscore data. So I've used the average formula, and the standard deviation, I use what formula? You can imagine. I use the STDEV-P formula. This is one of those cases where it's important that I use that P on the end because I'm designating this as a population. And you'll recall what that means, what's the actual calculation that Excel is doing. All right, so if I'm going to treat this as a population, this is the population mean, here is the population standard deviation. And we can take a sample, a random sample of size 15 from this population of fast food service times. And we can do that in StatTools. And what I'll actually show you is how to do that. But we're going to go even broader than that. What I'd like to be able to do is demonstrate a sampling distribution for you. And as you might imagine, I've got 200 members of my population. I'm taking samples of size 15. There's a very large number of possible combinations of 15 times that I could select. All right? And there are ways you can calculate this if you remember and have studied permutations and combinations, which we will not be going over here. You could calculate that number, okay? But there's a very large number in the thousands or even tens of thousands of the number of possible samples that you could come up with. And we won't be able to generate all of those. But I'll show you how we can generate 25 samples of size 15 from this population of 200 fast food service times. And we can do that within StatTools. So let's go ahead. And StatTools thinks for a while and then generates a series of samples. It's labeled time sample number 1, time sample number 2, all the way across to time sample number 25. And these are each a random sample. So each column here represents a random selection of 15 individual times from our list, from our population. And we could go ahead and calculate the mean of each of these samples. And that's really what would make up our sampling distribution of sample means. The sample means of each one of these 25 samples plus all the other possible samples that could be taken. So we could do that fairly easily in StatTools. We could actually use our summary statistics, or we could use our average formula with a little bit of manipulation because we're working on StatTools output. But that's easy enough for us to do, to come up with the sample means. And what we want to do is take a look at all the possible sample means we could come up with. It turns out 25 samples is not quite enough to really do justice to the demonstration. So I've gone ahead on another spreadsheet and I've generated quite a few more samples, as we'll see. So I'm going to close this file and I'm going to hop over to another file to complete that demonstration. But what it's going to lead us to is some information about what the central limit theorem tells us. Because we have 25 samples here, we're going to look at a larger number of samples shortly, but what does the central limit theorem tell us about this distribution if we could ultimately look at every single possible sample of size 15? Well, it tells us that the mean of that sampling distribution of sample means would be exactly equal to mu, the population mean. So think about what we're saying here. The mean of all my sample means should be exactly equal to the population mean. And the standard deviation, the spread of this sampling distribution of all the possible sample means, is going to be given by this formula, this simple mathematical formula, to use a term from our videos. Sigma, which is the population standard deviation, divided by the square root of my sample size. Now these terms come out of some mathematics behind this distribution. Now we won't go into, as the video didn't, we won't go into the math behind this. But this is a result that comes out of the central limit theorem. But it tells us something very important. It tells us where the center of this distribution falls and what the spread of this distribution is. So if we can get a handle on those two things, that can tell us a whole lot. So let's take a look at what else we can find out about this distribution. The other thing the central limit theorem tells us that maybe we'll get a glimpse of is that this distribution is roughly normal. And again, this comes out of the mathematics of the central limit theorem that we won't go into, but let's see if we can demonstrate that by looking at not just 25 samples, but a larger number of samples from this same population. So I've taken our 25 samples that we just generated, but I've generated the sample mean for each of my 25 samples. And it's really these values of sample means that are going to make up the distribution. What I also went ahead and did was to generate another 25 samples and calculate another 25 sample means. And yet another 25 samples, and so on. I actually generated a total of 250 samples, just to give us a larger number, just to give us a larger number of sample means to look at in our demonstration. As you'll see, this still doesn't work out exactly perfectly, but it should give you an idea as to the consistency that comes out of the central limit theorem. And what I've collected here is all of these sample mean values, all 250 sample means from the 250 samples that I generated are captured up in this array. And hopefully that'll be enough to show us something of the results that come out of the central limit theorem. So each one of these represents a sample mean from a randomly selected sample of size 15 taken out of our population of fast food service times. So what is the mean of our sample means? I've recorded over here, by the way, the population mean and the population standard deviation that come out of our original list of times, just for comparison. So what's the mean of our sample means? I'll just use the average formula on my array of sample means. So I'll say equals average, and then I'll select all 250 of my values. Start with the upper left-hand corner, shift control down arrow, shift control right arrow. And that selects everything. We haven't done that yet on a two-dimensional array, but it works the same way. We've done it down a column, I think, and across a row. Well, I can just do the two of those together to select an entire rectangular array. Close parentheses, and this gives me the average of my sample means. And let's take a look at that value. We got 0.88921. And if we compare that to our population mean, 0.8806, as you can see, we're not too far off. If you think about each one of the sample means, they're all over the place. But when we take the average of a large number of those sample means, it converges very close to the population mean. And I would propose to you that if instead of 250 sample means here, I had 2,500 sample means, the mean of those sample means would actually converge much, much closer and ultimately right at the population mean of 0.8806. But as you can see, just with 250, we get very close. If you try this with just 25, you'll see that you're maybe only a little further away, but you'll still be in the ballpark of the actual population mean. So hopefully I'm able to do a slightly better demonstration with 250 samples. So this tells us something important about where does the center of this sampling distribution lie. And what about the spread? What about the standard deviation of the sample means? Now, again, we're not thinking about the population standard deviation or the sample standard deviation, but the spread, the standard deviation of all the possible sample means of samples of size 15 taken from this population. All right, so I'm looking now at the standard deviation of this sample means. I'm going to use the STDEV formula on this list of this array of sample means. So equals STDEV. Again, I'll select my entire array, close parentheses, and I get a value of 0.11944. Okay? That's the standard deviation of the sampling distributions. Now, what did the central limits theorem say about how this would relate to the population standard deviation? Well, the central limit theorem said it would be equal to the population standard deviation divided by the square root of the sample size, square root of n. So let's see how this actually works out. I have my population standard deviation here. My sample size is 15. So let's calculate this. And as we'll see, it's called the standard error. And I'm going to build the formula equals my population standard deviation, sigma, divided by the square root, SQRT, of my sample size, n. And I end up with a value that you see is very close, once again, not exactly on, but very close to my standard deviation of the sample means. So hopefully we've seen just from a collection of 250 samples that the mathematics that's borne out by the central limit theorem really does hold fairly consistently. It does hold fairly true. And what does this mean? What does this allow us to do? We now have a distribution, and this is what gets really powerful. We now have a distribution of all of the possible samples that exist out there of size 15 taken from this one population. We know where that distribution is centered, and we know the standard deviation of that distribution. Okay? As we know from our earlier discussions, we know a lot if we know the mean and the standard deviation of any distribution. Now, a lot of our discussions have centered around bell-shaped distributions, and we talked specifically about the normal distribution. Well, the central limit theorem also tells us that this distribution should be normal, roughly normal. And just to look at this, I took my 250 sample means, and I attempted to generate a histogram, just to give me a rough idea. And this is what the histogram looks like. Now, you could look at this and say it looks like it could be somewhat normal. Again, I have only 250 samples captured here. So it doesn't look perfectly symmetrical and bell-shaped, although it's actually close enough. And later on, we will do a test for normality. And as we'll see, this is actually sufficiently symmetric to be considered normal. So this tells us all the things we really need to know about this distribution. The shape, it's bell-shaped, it's sufficiently symmetric actually that we can treat it as being normal. So we can apply things we know about the normal distribution and the formula we know to calculate probabilities around the normal distribution. So the shape is very important to us. Secondly, we know where the mean is. We know how to calculate the mean. It's going to be exactly equal to the population mean. And we know the spread. We know the standard deviation, called the standard error, of this sampling distribution. And that allows us to know some important things about the distribution. Now, why is that useful? Well, it's useful because when we try to estimate the population parameter, we're going to go out and take one sample. Well, what do we know about that one sample? We'll get to that in a second. I have a whole slide dedicated to that. Let me just express in symbols what we've seen from the central limit theorem. Okay, the expected value of x bar, right, the mean of this distribution of sample means is going to be exactly at the population mean, and the standard deviation of x bar, the standard deviation or spread of my sample means, is going to be given by population standard deviation, sigma, over the square root of the sample size. And we call that standard deviation of x bar, we call it the standard error of the mean. And so when you hear standard error, we're talking about the standard deviation of a sampling distribution of some sample statistic, in this case, the sample mean. Well, what do we know about that spread? What does that spread tell us? It is a standard deviation, so it tells us the same things that standard deviations have always told us. It turns out it's a measure of the accuracy of our estimation process, because the standard deviation is going to be the typical spread, the typical deviation of any point away from the mean. That's true for any distribution. But if you think about it in the context of a sampling distribution, well, any point in that distribution might be the one sample that we've taken and the one sample mean that we've measured. Well, what's a typical deviation between that value and the actual population mean, which is the center of that sampling distribution? Well, that's going to be our standard error, our standard deviation of the sampling distribution. So it's an important measure of the amount of accuracy in our estimation. If the standard error is very small, then that implies that the possible deviations that we may have in our actual sample mean away from our population mean are very small. If the standard error is very large, that means, hey, there's a lot of variability as I go from one random sample to the next random sample, meaning I have less accuracy in my estimate. So it's a measure of variability, just like all standard deviation. The smaller standard error implies a more accurate estimate. And as you might remember, a smaller, back up to that slide, a smaller standard error, think about the formula that we just saw. Standard error is sigma over the square root of n. So the sample size is in the denominator. So what that means is, just like we were saying for reducing sampling error, if the sample size gets larger, the standard error is going to shrink, and that means our estimate is more accurate. So the larger the sample size, the more accurate our estimate. So how does this help us estimate a population mean? And hopefully you're already able to put all these pieces together in conjunction with the video that we watched that also helped do this. If we have one sample, which is usually the case, of a specific size n, what do we know about its sample mean? Well, its sample mean is 1 point on a normal distribution that's centered at mu, at the actual population mean, and has a standard deviation that we could calculate as sigma, the population standard deviation, divided by the square root of n. So we know the mean, we know the standard deviation, the standard error, as we'll call it in this case, and we know that it's a normal distribution. So we can calculate all kinds of probabilities. We know that, for example, there is using the empirical rules, a 95% chance that this one observation is within plus or minus 2 standard errors from the population mean. And that's where our video led us, and that gives us the basis of a 95% confidence interval. Just from our other empirical rules, we're 68% sure that the distance from the sample mean to the population mean is within plus or minus 1 standard error. We're 99.7% sure that the distance between the population mean, the thing we're trying to get, and this one sample mean that we have is within plus or minus 3 standard errors. So we can apply all the things we know about distributions that are roughly symmetrical shaped to know some very important things about this particular population and how far away our actual sample mean is from the population mean. And that's really the crux of the issue in trying to come up with a confidence interval. Because if my sample is, I'm 95% sure my sample is within plus or minus 2 standard errors from the population mean, that means I'm 95% sure that the population mean is within plus or minus 2 standard errors of my actual population mean. So the distance between them is within plus or minus 2 standard errors, to a 95% level of confidence or surety. So I can take the one sample that I know something about, and I can just turn the logic around and say that, hey, I'm 95% sure that my actual population mean falls within this range. As we'll see, we're actually saying something slightly different when we define a confidence interval. What we're really saying is that I'm 95% sure that this one sample I took is one of those that would be between plus or minus 2 standard errors away from the population value, from the population mean. What we can think about it logically as being 95% sure about a region within which our actual population mean lies. Few words on estimates, point estimates and interval estimates, because this is where we're going when we start talking about confidence intervals. A point estimate is kind of our best guess when we're doing inferential statistics. It's kind of a single value that's our best guess of this population parameter based on the sample statistics. So in our case, it'll be our sample mean. We take our sample mean and, hey, for the one sample that I've gotten, that's my best guess at what the actual population mean is. What about an estimate of the interval? Well, it's some range around that best guess, around that point estimate, that we can have some degree of confidence that the actual population mean lies, or whatever parameter we're interested in. So it's some range around the point estimate. And we call that interval estimate the confidence interval. So I have my point estimate plus or minus some interval on either side, within which I can be perhaps 95% confident that the actual population value will lie. So this is how we build up a confidence interval, from a point estimate plus or minus some interval on either side. And then there are good estimators and less good estimators, and let's talk about those. An unbiased estimator, there are two terms I'm going to introduce here, an unbiased estimate and something called a consistent estimate. An unbiased estimate, or an unbiased estimator, is a point estimate, as the slide says, for which the mean of the sampling distribution equals the actual value of the population parameter. And this was true based on the central limit theorem for the sampling distribution of sample means, right? Where the mean of the sampling distribution of sample means was exactly equal to the population mean. So this would imply that sample mean is an unbiased estimator for population mean, because the mean of that distribution falls exactly at the population mean. This is not true for every sampling distribution. It's true for the sampling distribution of sample means, but not true for every sampling distribution. So not every estimator is an unbiased estimator. And even if you have an unbiased estimator, some of those may or may not be what are called consistent estimators. So a consistent estimator is an unbiased estimator for which the deviation between the estimate and the actual parameter, so the standard error, decreases as the sample size increases. So if we increase sample size and that causes our standard error to shrink, again, as is the case with the sampling distribution of sample means according to the central limit theorem, then our estimator is also considered a consistent estimator. So X bar is both an unbiased and a consistent estimator for mu, for the population mean. Because you'll remember the formula, the standard error is sigma over the square root of n. So as n increases, sample size decreases. So that covers a lot of information about this sampling distribution and how we're going to use it to go about doing inferential statistics, mainly on estimating population means. We'll also look at estimating population proportions in this class. And your textbook goes into a few other population parameters that can be estimated. And we'll see later on in the term how we use this same sampling distribution to do something called hypothesis testing. Well, what else do we not know? The central limit theorem told us a lot. It told us the shape of the sampling distribution for sample means. It told us where it's located. It told us a formula by which we could calculate the standard error, the spread of that distribution. But if you're following along really closely, and again, the video drew reference to this, there's still something we often don't know. Remember, in the practical world, we've taken one sample. We can't measure the whole population. We've taken one sample. We measure the sample mean. But our standard error formula requires us to know sigma, sigma over the square root of n. And sigma is the population standard deviation. We usually don't know that. So the video gave us some hints. It said we could go back and look at historical data and get some information from that. Or we could take a test sample of size 30 or more, and we'll see the significance of that 30 number. What is that? Why 30 or more? Or we could actually just take the standard deviation of the sample that we have and substitute that for the population standard deviation sigma. So one method that's often used is take our sample, especially if it's a sample over size 30, substitute that in place of sigma. As we'll see, it doesn't even have to be for a sample over size 30. So we end up getting our standard error formula, the standard error of X bar being equal to S over the square root of n, two things that we know or can easily get. Once we have our sample, we've measured the sample mean, we can easily measure the sample standard deviation, and we know our sample size. So from that, we really have in front of us everything we need to know to do important calculations about this sampling distribution, about where our sample lies relative to the entire distribution with some degree of confidence. And that is the basis of all of inferential statistics, as we'll see. Everything else is mere detail. But as the slide says, it's about 6 weeks worth of detail. So hang around for the second half of the class, and we'll use what we've just learned about sampling distributions to dig in and actually do inferential statistics. So where we are now is having introduced sampling distributions and sampling. The rest of this module on statistical inference is going to have us go through confidence intervals, have us build hypothesis tests and conduct those, and that's where we're going.